Welcome students, myself Dr. Govardhan Edu, Assistant Professor Physics, Government Rajiv Lochan College, Rajim. Today I am going to deliver a video lecture on Einstein Coefficient in laser theory. In the previous video lectures, we had discussed about the process of laser action. There are three main processes in the laser system: absorption, spontaneous emission and stimulated emission. For the better laser action, we need the prominent stimulated emission. So from the laser theory we can see that how the stimulated emission can be maximized, how the Einstein coefficient play the role to enhance the stimulated emission. In this lecture we discuss about the relation between the Einstein coefficients, and from that relation we achieved the laser theory. So let us start with the Einstein coefficient in laser theory. Let us consider an external environment. With energy density U of nu. In between them there is energy states. It's called E0 and E1. Here there are number of particles in those E1 and E0 energy states. Let us assume that the N1 particle belonging to E0 energy state and N2 particle belonging to E1 energy state. And in the external environment there are number of particles of frequency like nu. So the concentration of the external environment particle are very high. In between the energy states E0 and E1 there are three probabilistic processes can be occurred: absorption, spontaneous emission and stimulated emission. These are the process or the statistical process. These are the process of probabilistic process. So we cannot counted the number of particles in E0 and E1. Only we can say that there is a possibility to transit E0 energy level particle to the E1 level particles. So the transition from E0 to E1 and E1 to E0 is totally probabilistic. That's why we can use the Maxwell-Boltzmann statistics to find out the Einstein coefficient. In this section, the rate of spontaneous, rate of stimulated, rate of absorption will be discussed, because we cannot count the number of particles in the whole system. So from the Maxwell-Boltzmann statistics we can write n proportional to exponential of minus e by kt. This is the Maxwell-Boltzmann statistics probabilistic equation. One thing I will also discuss here: the energy levels of atoms E0 and E1 and the external environments are in thermal equilibrium. So the temperature is nearly constant in the external environment and the energy states. That's why we can use the Maxwell-Boltzmann statistics. When the thermal equilibrium systems comes into picture, the Maxwell-Boltzmann statistics follow, and from that we can write n proportional to exponential of minus e by kt. From that equation we can write the value of n1 and n2 in this form. So we can write n1 proportional to exponential of minus e1 by kt and n2 proportional to exponential of minus e0 and after e1 by kt, here e0 and e1, and the ratio of that can be written as n1 by n2 is equal to exponential of e1 minus e0 upon kt. But the difference between e1 and e0 is equal to h nu, because when the particles in energy state e1 undergo to e0 by the spontaneous or stimulated, they can emit light of h nu form. So the difference between e1 and e0 is equal to h nu, and we can write n1 by n0 is equal to exponential of h nu by kt. So here we can write the rates of spontaneous, stimulated and absorption, because these are the probabilistic process, and at a time one particle undergo from upward transition. At that time the downward transition can also be occurred. So all these three processes occur simultaneously at a time. One particle go upward, at that time the another particle goes downward. So the process is simultaneously. Therefore we can write the rate of absorption, which is proportional to, which is indicated as R1, which is proportional to the number of particles exist in the ground state. Which particle can be absorbed? N1 particle. Those particles which belong to ground state, that can be possibly absorb energy from the external environment and goes to upward energy levels. So the upward transition can make when the particle gains some energy from the external environment. So rate of absorption R1 is proportional to N1, and it is also proportional to U. Here U nu can be written as here U nu can be written as U, because the particle need energy to undergo upward transition. The external environment play an important role. That's why the rate of absorption is proportional to mu. So R1 is equal to B12 N1 U. Here B12 is called Einstein absorption coefficient. So this is the first relation which comes from the rate of absorption. Similarly, we can write the rate of spontaneous emission. Here R2 is the rate of spontaneous emission. R2 is proportional to only the number of particles in the excited state, N2. So we can write R2 proportional to N2 because it is self emission, spontaneous emission. So there is no use of external environment for the particle to undergo from E1 to E0. That's why R2 is only depends upon N2, and we can write R2 is equal to A21 N2. Here A21 is called Einstein spontaneous coefficient. Similarly, we can write the rate of stimulated emission, which is denoted as R3, and which also depends on the number of particles in the excited state E1, that means N2, and for the stimulated emission we need external environment particle, induced particle, which is equivalent to the excited state particles in respect of energy, frequency, phase and direction of polarization. So R3, rate of stimulated emission, proportional to N2 as well as U. Which particle stimulated? N2 particle, which is situated in a E1, or which particle stimulated? The N2 particle which belong to E1 energy state, and the external environment particle. So R3 is equal to B21 and 2U. Here B21 is called Einstein stimulated coefficient. Here we can calculate R1, R2, R3, rate of spontaneous stimulated and absorption. All these three processes are related by this equation. R1 is the rate of absorption. This is the upward transition. And R2 plus R3. R2 and R3 are the spontaneous and stimulated rates. These are the downward transition. In thermal equilibrium, the upward transition is equal to the downward transition, or the total rate of change of the particle should be equal to 0 in thermal equilibrium. In other sense, we can write R1 minus R2 minus R3 is equal to 0. This is the total rate of change of the particle, which should be 0 in the thermal equilibrium. So R1 is equal to R2 plus R3. Now put the values of R1, R2 and R3 and get a proper suitable relationship between the Einstein coefficients. R1 is equal to B12 N1U is equal to A21 N2 plus B21 N2U. Here we can see that the ratio of N2 by N1 is equal to B12U upon A21 plus B21U. Now, as in previous discussion, the ratio of N2 N1 is calculated. So this is equal to exponential of minus h nu by kT. So now we can calculate the value of U, which is the energy density of external environment. Therefore, we write B12U exponential of h nu by kT is equal to A21 plus B21U, and U is equal to A21 by B12 exponential of h nu by kT minus B21. Now the manipulated equation of mu is A21 by B21 upon B12 upon B21 exponential of h nu by kt minus 1. This equation is similar as the Planck radiation formula, so we can compare this equation to the Planck radiation formula. The Planck radiation formula is is 8 pi h nu cube by c cube into 1 upon exponential of h nu by kt minus 1. So compare these two equation, we get A21 by B21 is equal to 8 pi h nu cube by c cube. This term is equivalent to this term. The numerator of u is A21 by B21, which is equal to the 8 pi h nu cube by c cube, that can be written here. And in the denominator, here the ratio of B12 by B21 multiplied by the exponential term. Here the exponential term multiplied by the factor 1. So B12 by B21 is equal to 1. This is the important relation. Now here we can see that the B12 is equal to B21. B12 is equal to B21. The Einstein stimulated coefficient should be equal to the Einstein absorption coefficient. That indicates the absorption process is called the stimulated absorption. So in the laser action, not only the stimulated emission is enhanced, but the process of absorption can also be enhanced. In the second relation, A21 by B21, which is equal to 8 pi h nu cube by c cube, this also gives very useful information about the radiation. This is written as h by lambda cube. From these relations, we easily achieved the laser theory. Now we can write R3 is greater than R1 and R3 greater than R2. R3 is the rate of stimulated and R1 is the rate of absorption, R2 is the rate of spontaneous emission. For the better laser action, for the efficient laser action, for the efficient laser light pulse, we have to maximize the rate of stimulated emission. That's why we consider these inequality equations. How can maximize the rate of stimulated emission in this laser system, in the laser systems. So R3, put the value of R3, R1 and R2 and get a desirable condition which is totally responsible for the better laser action. R3 is the B21 and 2U, which is greater than R1, B12 and 1U. Here we cross B21 by B12 because these are the equal and U of U cancel out. So N2 greater than N1. The number of particles in the excited state is greater than the number of particles in the ground state. So the population of the particle is invert. In the ordinary lights, the number of particles in the ground state is greater than the number of particles in the excited state. But in the case of laser action, we change the polarity of the number of particle, and we need the number of particle in the excited state and the number of particle in the ground state in the following relation. This relation is called population inversion. So achieve the good laser pulse, the population inversion is established in the laser system. This population inversion is also called negative temperature state. Negative temperature state. Why it is called negative temperature state, it will be discussed later. Here the first main criteria for the laser action is to achieve the population inversion condition between the transition levels. Now comes to the point negative temperature state. Here we can explore this condition N2 greater than N1. Write the value of N2 and N1 again here. So N2 is equal to C times exponential of minus E1 by KT, greater than C times exponential of minus E0 by KT. In the starting section, we write the value of N1 and N2 in this form. So CC cancel out, and exponential of minus E1 plus E0 upon KT is greater than 1. We also write the value of minus E1 plus E0 is minus h nu in starting section of this lecture. So the desirable condition can be reduced to exponential of minus h nu by kt greater than 1. Here h is the Planck constant. The value of Planck constant is equal to 6.6 into 10 to the power minus 34 joule second, and K is the Boltzmann constant. And the value of K is 1.38 into 10 to the power minus 23 joule per Kelvin. And T is the thermally equilibrium temperature between the energy states and the external environment, and nu is the frequency. So now talk about this term. This term should be equal to 1, but this term is the negative term. Here h is the constant, k is the constant. That can be the numerical constant which cannot be changed, so we cannot alert these values. And T is the thermal equilibrium temperature, and nu is the frequency. Frequency cannot be negative in physics, so h, nu, k, these three quantities cannot be altered. This cannot be treated as negative, so only one term can be left here, T. When put the value of T in a negative sense, then this term becomes greater than equal to 1. So we can say that in theoretically but not in experimentally, the negative temperature state called because the temperature treated as negative in this condition and hold this condition and 1 greater than to 1. So population inversion condition comes to this negative temperature state. This is the first condition for the better laser action. Now comes to the second condition R3 greater than R1. The value of R3 is equal to N2 U and B21 R2. A21 N2. So N2 and N2 cancel out, and U B21 by A21 is greater than 1. Let us look this inequality equation. U and B21 by A21 ratio should be greater than 1. The U is the energy density of the external environment. So for the maximize the value of U, means energy density, we should arrange the resonant cavity arrangement in the laser system. So the active medium is placed in between the parallel plates, out of which one is partially reflector and another is totally reflector. Because when one of the particle is emitted from the metastable state to the ground state by the spontaneous emission, cannot be emitted from the laser source, which is totally responsible for the stimulated emission. Means spontaneously emitted particle can induce the excited state particle to stimulate the particle and undergo to the ground state and emit same frequency, same phase, same direction of polarization particles. And to enhance this condition, the concentration of the stimulated particles is higher in the partially reflector end. So the resonant cavity is the important arrangement for the better laser action. So B21 by A21 is greater than 1. B21 is the rate of stimulated and A21 is the rate of B21 is the Einstein stimulated coefficient, A21 is the Einstein spontaneous coefficient. This ratio should be greater than 1. So in the laser system, level which is called metastable state level formed, which is totally responsible to allow the particle to stimulate from upper level to the ground state level and doesn't allow the spontaneous emission. So the metastable state belongs to this ratio B21 by A21. From the metastable state, the stimulated emission possibility is maximum and the spontaneous emission possibility is minimum. So the spontaneous emission is forbidden and stimulated emission is allowed from the metastable state to the ground state. So there are three conditions which is totally responsible for the laser action and which is called the laser theory. First, the population inversion. The number of particles in the excited state is much greater than the number of particles in the ground state. Second, in the laser system, we can set up the resonant cavity. It is the arrangement of the two parallel plates, out of which one is perfect reflector and another is partial reflector. And third one is the metastable state, which is created with itself by the system. It doesn't create by the human beings. In the laser system, the metastable state is created by the system itself, and it is the temporary and virtual state that can be physically defined as the state where the spontaneous emission is allowed, spontaneous emission is forbidden, and stimulated emission is allowed. So because of the stimulated emission is allowed, we can get same frequency, same phase and same direction of polarization particle from the laser source. So in the laser theory, we can discuss between the Einstein coefficient, and for the maximize the stimulated Einstein coefficient, we have to set up the population inversion, resonant cavity, and the metal stable state in the laser system. Thank you very much.